Okay, hey everyone, welcome back. So what we're going to do in this video is going to start talking about reactions. Okay, so reactions that we're going to encounter in organic chemistry. And right now, the reaction that we're going to deal with is in chapter 10. Okay, and this may sound weird because now we've suddenly skipped a few chapters and we're in chapter 10. And that's because I'm trying to do this in a logical order or build complexity into the reactions that we are doing, the ones that we'll be talking about. So in chapter 10, what we're going to do is we're going to learn about reactions of alkanes. Now, realize that these are the simplest of the hydrocarbons because they only contain carbons and hydrogens in them, or at least that will be our focus. Only carbon-hydrogen bonds, and it should be carbon-hydrogen sigma bonds, no pi bonds, okay? Or in some sense, if I were to simplify this, I can say that this is the chemistry of sp3 hybridized carbon. So we're going to start with the chemistry of sp3 hybridized carbons. Now, the reaction that we're going to learn here in this chapter, okay, we're going to learn how to convert an alkane, okay, into an alkyl halide. So this will be the next group of compounds that we'll be dealing with. So we will learn this chemistry of alkyl halides in chapter 7. Now in chapter 7, we're going to see how alkyl halides react in two ways. One is substitution. Okay, this will help us put functional groups. So basically add functional groups to an alkane. So we will get something like an alkyl with a functional group. Notice how what we have here is an alkyl with a halide. Okay, so we sort of have an alkyl halide. Now we're going to learn how to substitute that halide with some other functional groups. So we're going to learn how to add functional groups so that we get alkyl with a functional group attached to it. Now the other kind of chemistry that we're going to learn for alkyl halides, this is going to be elimination. Okay, and elimination is going to give us alkenes and alkynes. Okay, and this basically leads us into then chapter 8 and chapter 9, where we're going to learn more about alkenes and alkynes after that. So that's why I'm doing chapter 10 right now. So this is in chapter 10. Okay, the reactions of alkanes, and we're going to start small. Alkanes, they only do few reactions, like in terms of number. Okay, and then alkyl halides, they pretty much do reactions that can be categorized into two broad classes: substitutions and eliminations. And then what you will see is once we go to alkenes and alkynes, they do reactions that are classified as addition reactions, but there are like a ton of them. That's where we're going to see the bulk of the reactions. And I think it's also good to kind of categorize and arrange it in this manner in your head, because this would help us to think about reactions that will be useful to produce, let's say, an alkene from an alkane. This is all stuff that's coming later, more complicated, okay? But right now, we're going to start with the reactions of alkanes. That's in chapter 10. Okay, so chapter 10, this is reactions of alkanes. Now, I think we can talk about two reactions of alkanes, but again, one, I'm just going to briefly mention it. It's the other reaction that we're going to focus on, okay? So one reaction of alkanes that we can kind of briefly talk about or mention here is a combustion reaction. Now, realize that a combustion reaction is where you take an alkane, and alkanes are represented by this general formula, CnH2n plus 2, where n is an integer, okay, so some integer. When alkanes, combustion is basically burning compound, so when alkanes react with oxygen, this is going to produce n molecules of carbon dioxide. Now, I'm not writing a balanced equation here, okay, so I'm not saying how many oxygen molecules here, but this should produce n molecules of carbon dioxide, and it's going to produce n plus 1 molecules of water from every alkane in some sense, okay, n plus 1 molecule. So let's look at an example here. So C2H6 ethane, okay, this is CH3CH3. If we take ethane and react it with oxygen, which is basically the combustion reaction, this is going to produce 2 molecules of carbon dioxide because there are 2 carbons in ethane, and plus there are 6 hydrogens, so it's going to give us 3 molecules of water. So you can see how it always produces n plus 1. So n here is 2, that's the integer, and it produces n plus 1 molecules of water. Now you can do a simple math and back calculate how many oxygens needed here, okay? I'm not filling that in, but it's some number of oxygen atoms which can be easily derived from that number here, and you might have to like balance the equation further. That's a different story, but that's one simple reaction of alkanes. Simple but very important, because this is the reaction that allows us to use alkanes as fuel. For example, you know, we use natural gas, we burn natural gas in our homes for heating and everything, and this is pretty much the reaction that's going on, okay? Natural gas, which is methane, is combusted, it is burned. We burn gasoline in our cars. It's again the same reaction. Those are alkanes, and those are basically combusted to produce energy, because whenever we do this reaction, this releases energy, and we can harness the energy to do different kind of things, okay? So that's one reaction of alkanes. Now, the more important reaction, because as you can see here, we take the alkane, we burn it, produces carbon dioxide and water. The carbon in your compound becomes carbon dioxide. Now, and potentially, you can take carbon dioxide and do different things with it, but as far as organic chemists are concerned, I think we would like to take the alkane and keep the hydrogen and the carbon. So if it's a CH3 and a CH3 in ethane, we would like to keep most of it and take it to other things, to make other things from this, okay? So that is what we're going to see in the other reaction. Okay, so the other reaction, slightly more complicated, and the more important reaction of alkanes, okay? The second reaction is called a free radical halogenation. A free radical halogenation. Now, as the name suggests, the reaction involves radicals. And in an earlier video, we actually looked at what radicals are. We talked about radicals to some extent. We'll see them again in this video. But what happens in this reaction is, this is the reaction of an alkane, with halogens, okay? Now, usually the halogen is a dihalide molecule. When we talk about halogens, we're talking about fluorine, chlorine, bromine, iodine, so those halogens. And when we say a dihalide molecule, we are referring to something like F2, Cl2, Br2, I2, all of these molecules. Okay, with a dihalide molecule, to produce alkyl halide. So that's our product. So we're going to make an alkyl halide. So our reactant is an alkane, and the halogen and the alkyl halide is the product from this reaction. Okay, an example for this reaction is, let's say if I represent an alkane by RH, okay, this is an alkane. And realize that this notation is perfectly all right, because R is an alkyl group, and it is obtained by removing a hydrogen from an alkane. So if I add a hydrogen to an alkyl group, that is an alkane. So if you react an alkane with an X2, where X is a halogen. Now, this reaction usually requires heat or light. So H nu is light, and we represent heat by this delta, capital delta symbol. Okay, so that's the big delta. So heat or light for doing this reaction. And the product from this reaction is Rx plus Hx. Okay, so that's a very generalized scheme for this reaction. So RH plus X2, X2 realize is X and X. So essentially what we're doing in this reaction is we're breaking this bond here, we're breaking this bond here, and we're making two new bonds. We're making two new bonds. So that's a new bond, this is a new bond. Okay, so we are breaking here. This is breaking, and this is form. So you're forming bonds over there. So you're breaking some bonds, and we're forming some other bonds overall here. Now, so that is a very generalized reaction where an alkane reacts with a halogen in presence of heat or light to give you, sorry, I should write this, an alkyl halide, okay, an alkyl halide, and plus a hydrogen halide, HX, like HCl, HBr, compounds like that. And alkyl halides, as I mentioned earlier, these are important because now these can do other reactions. Okay, so alkanes can be converted into alkyl halides, and alkyl halides can be converted into other compounds. A specific example, okay, a more specific example for this, we can probably use methane, CH4. So CH4, this can react with, let's say, Cl2 in presence of light, and it can give us CH3Cl plus HCl. So CH4 is CH3H. So you're breaking the bond here, breaking the bond between the two chlorine atoms, and then you're making methyl chloride plus HCl. Now, this reaction does not have to stop here. This can react further with more Cl2 in presence of HNu. So what I'm trying to say here is now, I think as we work through this, also get used to reading these reaction arrows so you can see these written in several ways. So do not get confused. They're all meaning the same thing. What I'm trying to say here is methane reacts with chlorine in presence of light to give me methyl chloride plus HCl. And then I'm saying that methyl chloride reacts with more chlorine in presence of light. And now if I do this, what I should get is CH2 now, and then Cl2, because there's another carbon-hydrogen bond that's breaking, and it would give us HCl. And this reaction basically can continue on, okay? This can keep going till you exhaust all the hydrogens in that alkane. So you can pretty much break every carbon-hydrogen bond. That's a possibility if you do not control this reaction, okay? So usually we have to control the reaction. So this can basically keep going like that till you finally form, okay, the final product that you're going to make is going to be CCl4. So carbon with 4 chlorines attached to it. Okay, so that's an example of a halogenation reaction. Now, the reaction here, so this is a halogenation reaction. The mechanism of this reaction is what we're going to look at next. Now, when we say a mechanism, in chapter 6, we said that, you know, when reactants become products, you have to break some bonds and you have to form some new bonds, but they don't happen simultaneously. Not everything is happening at the same time in one step. So it's not a simultaneous process. In fact, there's a name for this. It's called concerted, which we will come to later. Okay, so this does not happen in one step. A reaction like this may have several steps before the reactants become products. So the mechanism of a reaction gives us a breakdown of those steps. How do you start from, so it kind of tells us, okay, what happened in going from the reactants to the products? What are the elementary steps? Like what happens first? What happens second? What happens third? Or what's the last step? How did the reactant molecules become products? Okay, so the mechanism kind of gives us a picture, an idea, or it gives us something visual to look at to understand what must have happened in going from the reactants to the products. So we'll look at the mechanism of this reaction next. Okay, so again, free radical halogenation is what we're still talking about. And we'll talk about the mechanism of this reaction. Okay. So in terms of mechanism, it is believed that, or not believed, don't just believe, okay, it has been shown, okay, as scientists, we don't just believe, we tend to like actually experimentally prove things, you know. So it is shown that, it has been shown that the reaction proceeds through 3 steps. The first step is called an initiation step. It's called an initiation step. Now, an initiation step is what starts the reaction, initiates the reaction, as the name suggests. And what happens in this reaction is, or what happens in this step is, the chlorine molecule, I think what I just realized is I think I should write the reaction that we are actually focusing on. So we're talking about this reaction where methane plus Cl2 in presence of light, okay, H nu gives methyl chloride plus HCl. That's the reaction that we're focusing on. Okay, so we're talking about the mechanism for this reaction. So in the first step, what is hypothesized or has been shown is that the chlorine molecule undergoes a homolytic cleavage. So these terms kind of should sound familiar based on chapter 6. Homolytic cleavage means when a bond splits equally between the two components. Okay, and so when you're breaking a bond, you need energy for doing that, and that energy is coming from this light, H nu. That's what's giving the energy for doing this reaction. So this bond splits homolytically. So there are 2 electrons in this bond. Each one goes to each chlorine atom. Okay, so I'm going to show it using this single-headed arrows, which are also called fishhook arrows. Okay, so 1 electron goes to each of the chlorine atoms. So I've shown that using this electron push here. So if I did this, what I should get is I should get 2 now chlorine radicals. Okay, so these are radicals now. So I get a Cl dot. So that's a chlorine with an unpaired electron on it. So that's a chlorine radical. Subsequently, so that's the initiation step. Subsequently, the second step here is called a propagation step. Propagation step. What happens in this step is the chlorine radical, it's a chlorine with 1 unpaired electron in it, reacts with methane. So I'm going to write the methane as HCH3. It reacts with methane. So it's going to react with this carbon-hydrogen bond here. So the chlorine radical brings an electron. And this bond between the carbon and the hydrogen, now that breaks homolytically. So the electrons split. 1 electron goes to the hydrogen. And essentially what I'm trying to say here is that the hydrogen takes that electron and pairs it with the electron from the chlorine. The other electron in this bond goes to the carbon atom. Okay, so the chlorine had 1 electron. Hydrogen took 1 of the electrons from that bond and it paired with the chlorine atom. And what that should give me is HCl now, a new bond between H and Cl, because a bond is 2 electrons. Chlorine brought 1 of the electrons, hydrogen brought the other electron. Notice how each arrow here is a single-headed arrow. So it's a fishhook kind of arrow. And so this reacts, and this would now give me a methyl radical. So there is a unpaired electron on that carbon now, which it got from this bond cleavage. Okay, so it gives a methyl radical. And then the methyl radical can react with more chlorine. Now this is a reaction. So we don't do a reaction by taking just 1 molecule of chlorine and 1 molecule of methane. We take a few moles of these compounds, which now contain several Avogadro number of molecules. Okay, so there's a lot of molecules around. So one of these methyl radicals that's formed, this reacts with another chlorine molecule, so Cl2, whatever started the reaction here. The carbon brings its electron. The bond between the 2 chlorine atoms cleaves homolytically again. So the chlorine brings 1 of the electrons. The other electron goes to the other chlorine atom. And what this gives us is now CH3Cl, where there is a bond between or if you prefer it, it doesn't matter. You can draw it either ways, but you can draw it like that to show that there is a bond between the carbon on the methyl group and the chlorine atom. They share an electron, and plus it gives us another chlorine radical. So these two steps together are called propagation steps, because these are the steps that propagate the reaction. Okay, and notice what happened at the end of this second propagation step. In this step, we generated a chlorine radical. And so what this chlorine radical can do is it can go back, react with more methane in the system, and make more HCl and methyl radical. That methyl radical is going to react with more chlorine in the system, make methyl chloride, which is our product, and chlorine radical. And then the reaction basically keeps going on, almost like a chain reaction sort of a thing. Okay, so it's almost like a chain reaction, or it is a chain reaction actually. But if you're familiar with the concept of chain reaction, like nuclear reactions, this is pretty much the same thing going on here. The reaction basically keeps going on and on. And between the two propagation steps, also notice how we've made both of our products. We made HCl in the first propagation step, and we've made methyl chloride in the second propagation step. Now, there is a third step which we will not spend too much time on, but the third step is called a termination reaction, or a termination step. Now, this is what ends the reaction. Okay, so what can happen in a termination step is a methyl radical can react with another methyl radical. They both bring electrons, and if that happened, we will get CH3, CH3. So we'll make some ethane now. Or a methyl radical can react with a chlorine radical to give us CH3Cl, which is our product. Or a chlorine radical can come in contact with another chlorine radical to give you Cl2. So the termination reactions, these usually happen like at the end, when the reaction is almost done. And what we mean by that is there isn't much reactant left behind. And so these do not contribute a lot to how much product is formed or how much ethane would be there in your reaction mixture. These are like, these are kind of insignificant compared to like other processes that are going on here. So the more important steps here are the initiation step and the propagation step, which is the most important because this is where products are formed in this step. Okay, so products are formed in this step. That's the most important step here. So this is a mechanism of free radical halogenation. Now, we did it for a specific molecule, methane, reacting with chlorine, but we can expand this to other halogens, and we can expand it to other alkanes. We will see that in a subsequent video.